Thank you very much for a kind introduction, and also thank you all for coming just before the lunch. Of course, I'd like to thank the organizers, David Sia, for giving me an opportunity to give this keynote. Keynote at ICC is like, as a student, it's like a dream. So it's really appreciated. So today I'm going to talk about photocatalysis. I will continue the effort of this water splitting. But you might have noticed that my talk is not like photo is in parentheses. So something that I wanted to do today is to try to make it unique. I'm not focusing on semiconductor side, but I'm more focusing on electrolyte and electrocatalyst on the outer surfaces and try to bridge the efficiency, try to do how we can further improve this photocatalytic water splitting. So my team, I just want to acknowledge first that these are the hard-working my group, bit above 40 people right now with the internship students. 1/3 are international students, and I am really enjoying the discussion with them. And as Chairman introduced, so we are working on heterogeneous catalysis, not only photocatalysis, but also working on thermal catalysis and electrocatalysis. And now more focusing also, try to bridge between the gap between them. Yesterday, Yuri Roman was giving beautiful work about how to tune these potentials to accelerate the thermal catalysis. We're actually doing in a similar direction. And recent Jack's paper on the left is the connection between electrocatalysis and thermal catalysis. And today, I'm trying more to bridge between photocatalysis and electrocatalysis. Hope you find it interesting. So the topic is after these green power generations. Let's see if it works. Okay. So green power. So our current largest project is actually water electrolysis. And once we have green hydrogen, we're also working on thermal catalysis to generate fuels. And photocatalysis and this water electrolysis is trying to be combined today. So a little bit about this green power to green hydrogen by water electrolysis effort. So I've been working on this electrolyte engineering. It's non-extreme pH condition. What is important is not only the electrode material, but electrolyte is as important, or even more important sometimes, to work on it. And this water electrolysis project is with this GTEx Wing project. It's a team consortium coming from Japanese academia. 24 laboratories are involved, and I'm the team leader of this project. We just recently started. But today I'm going to focus on photocatalysis. And I support that the Professor Dolman's approach, that the powder system is the most scalable techniques in terms of photocatalytic approaches. So I'm going to talk about this photocatalysis, which is typically black box. You shine the light, you get the hydrogen or oxygen out, but you don't know what's happening inside. So I keep saying that let's do it more quantitatively. So how can we do it quantitatively? I don't go into details today, but I tried to summarize what I think is right is in a review paper with this ACS Catalysis 2017. Basically, what we need to do is to identify the crucial properties, and separately, you quantify all this, and then try to connect it for the photocatalytic reactions. So for this audience, I will briefly going to it. But what I want to emphasize here is what is important. What is the catalyst component for water splitting is electrocatalyst, often called co-catalyst on the surface. This requires overall potentials to drive hydrogen evolution and oxygen evolution. And that is struggle with these band gaps between the semiconductor conduction band, valence band, and you have to make it smooth contact so that you don't lose this voltage created. So one important thing is electrocatalyst. So this I would like to emphasize today's talk. And we need to have a band edges that is matching with this electrocatalyst over potential. And we need to make a smooth contact. So if you try to break down into the process, I use this 6-gear concept starting from photon absorption, exciton separation, carrier diffusion and transport image be happening simultaneously. And it comes to the surface and it becomes electrocatalytic performance that can have a separate quantity, right, that you can quantify it. And I put the 6-gear. This has nothing to do with the photocatalytic material. This is electrolyte. Okay. This red gear, that's the mass transfer coming from ion diffusion. You know, even if you have perfect photocatalyst material, if you wrongly choose the solution, you're not working for the water splitting. Electrocatalysis, semiconductor, and interface. What about the time scale? So for this audience, I also don't need to go further, but this is, upper one is a textbook thing, and photocatalytic process dedicated, we can see how many properties you can separately quantify and try to understand where the bottleneck is. So starting from photon absorption in femtosecond, the catalysis is still happening in best millisecond, or even sometimes seconds order. So you have to fill the gap, but this process towards the end is also very important. What about spatial dimensions? So the molecule is in a sub-nano scale, right, water molecules. And the powder system is here. And if you think about the scalability, how to get the sunlight, we need to start thinking about how to scale up your materials in kilometer scales. You always have to consider, you know, how your device can be expanded to the kilometer scale. So now I'm focusing more on the bridging electrocatalytic knowledge to the photocatalytic knowledge. So photocatalysis, what you're doing is you're doing electrolysis of water in a nanometer scale, right? You shrink it between the distance between cathode and anode. Eventually, you're having nanoscale water electrolysis device. So if you translate that into this water electrolysis term, what is overpotential coming from? It's hydrogen evolution kinetic overpotential, oxygen evolution kinetic overpotential. Then it comes to solution side, where you have this pH gradient and solution resistance. And then you may have a crossover of the gases that may be additional loss. So here, actually, this is the electrode, or in this case, co-catalyst that you're putting. But here, additional part in yellow is actually coming from electrolyte. And that has nothing to do with the photocatalyst material. You can separately quantify the contribution of this overpotential coming from solution. So we really want to achieve 10% solar to hydrogen efficiency. So we can translate the target production rate also into the current density. So 10% solar to hydrogen efficiency is close to, well, the hydrogen evolution rate is 150-ish micromole per square centimeter per hour. That corresponds to about 8 milliamp per square centimeter. 8 milliamp per square centimeter to do actually electrolyzer. This is 1 square meter, and I'm trying to use non-noble metals, nickel and nickel, iron-based material. Actually, you're seeing the bubbles. I don't know if you see it. So this is achieving actually 1.6 volt and then 19 milliamp, which is already close enough to solar to hydrogen efficiency, 10%. But you can immediately notice that this electrode is completely black. You can't absorb light if you put this guy on top of the photocatalyst semiconductor materials. So this 1.6 can be translated to this visible light responsive. So it's in the border between visible light and infrared light. So you cannot do this because you need a completely black. So you need to have semi-transparent one. So you have to use somewhere like 600 nanometer. That is also reasonable in terms of band gap and additional overall potential required. So I translate for electrochemistry people. So we use this IV curve, or JE curve often it's called. So what is we need to target is 8 milliamp per square centimeter in both directions, hydrogen side and oxygen side. We need to have a good electrode material. This slope is sharper. If you have less quantity or bad electrocatalyst, of course, this slope will be longer, right? In this case, an oxygen evolution like this. So we need to have definitely a good hydrogen evolution catalyst, oxygen evolution catalyst, and we need to straddle the, this overpotential with these band edges. But again, if you use a poor one, you will never achieve this 8 milliamp per square centimeter. So first thing you need to do is to select the best electrocatalyst, especially when you want to use visible light materials, narrower band gap. Then we have this light absorption. Then you keep charging up this electrocatalyst, right, to maintain the steady state hydrogen evolution and oxygen evolution. That is because we have a multiple electron transfer. The same catalyst site has to keep doing the job for multiple electron transfer. So this hydrogen evolution catalyst or oxygen evolution catalyst need to sustain the potential. And that is at this potential that you want to achieve. So a little bit about fundamentals. I go into what is a true reactant for water electrolysis. So this, sometimes we learn at high school. So actually, what is the pH to begin with? So pH 0, let's assume the activity coefficient of 1. Proton is actually located here. How many water molecules surround it? It's actually 55 water molecules. It's a substantial amount of water per proton ions. pH 1 means you dilute to 10 times. pH 2 is another 10 times. So you dilute 10 times, 10 times. So the proton concentration, as you can easily imagine, that is highly diluted, especially if you work at neutral pH conditions or even pure water conditions. Here I have a OH minus. The story is the same. So OH minus is surrounded with 55 water molecules. And we need to start thinking about what is the reactant for hydrogen evolution reaction and oxygen evolution reaction. So in acidic conditions, we know that proton is the hydrogen source, and alkaline is switched to water. Oxygen evolution in acid, it's water molecule as a reactant. In alkaline, OH minus is sufficient that this becomes the reactant for oxygen. I will give you a typical example of what happens if you have a perfect hydrogen evolution catalyst, which is platinum electrode. And here we're trying to control the diffusion, so we use rotating disk electrode. So what we see here in the number corresponds to the pH. So pH 1, 2, 3, according to the Nellens equation, you shift 60 millivolts per pH. So you see hydrogen evolution current, current, current. Then what happens in the pH 4? You no longer have enough proton concentration in the solution. It becomes hydrogen, proton diffusion limitation has been observed. So you see this 10 to 5, it actually goes to the same trend because proton cannot be the reactant in these conditions. This is an unbuffered condition, so sodium sulfate that's used. 12, 13, you shift it again because the thermodynamics doesn't allow you to generate hydrogen at this potential. So here you can also see that local pH, if you start with even 5, the local pH close to the platinum is around 10. You can learn from this figure. So yes, there is a reactant switching from the protons to water. And you can see that the large overpotential is required if you work in the neutral pH conditions. If you switch a reactant to water, water is one of the most stable molecule. OH bond dissociation is quite challenging. So what you need to do in order to maintain the proton concentration in the neutral conditions, this is again high school chemistry, you can use buffer. Buffer can supply proton additionally, so you can see that this one is increasing the current as you expected from the pH positions. But we didn't stop here. Actually, this proton is carried by the buffer anion. So anion flux has to be maximized in order to improve this hydrogen evolution activity. Platinum is so good that platinum, once it comes, you pick up to generate hydrogen. So platinum is waiting for the proton to come. So then we use typical engineering approach, so steady-state approximation. So we can also divide into the properties. So here, one of the most important factor is viscosity of electrolyte, which has nothing to do with electrode materials. So this mu is the viscosity. So you can solve it for the steady-state approximation using this diffusion convection buffering action. And what you will see in these buffering conditions, the overpotential of hydrogen is actually not coming from the platinum kinetics. Platinum kinetics is so good so that it appears as if it is in a y-axis. Additional overpotential is actually, in this particular case, coming from hydrogen evolved, escaping from the electrode, because in these conditions, hydrogen oxidation also occurs. And additionally, this is the buffer contribution that you cannot be eliminated compared to acidic condition. So this is a local pH shift that we observe. So to summarize it for visuality, so here is what happens in the pH 5 or 4 conditions. If you don't know pH 5 is good electrolyte, and if you do hydrogen evolution using platinum, you have 500 millivolt over potential, because it's basically shift the pH and the water becomes a reactant. So now you know that buffer should be added. Little bit of addition, yes, you improve it, but it's not actually enough to supply this proton close to the platinum. You need to do this, we call it electrolyte engineering, to maximize the flux of buffer ions. So here the key word is reactant switching, contribution of diffusion, and pKa. pKa also certainly helps to minimize this pH gradient. So if we learn these kind of things, in ideal case, it's completely static conditions without any convection. Actually, if you want to achieve this 10 milliamp per square centimeter that we say we want to achieve, then the proton concentration has to be pH 1.6 or even lower. Highly acidic condition can be the only condition that you can use. Likewise, if you want to maintain OH minus as a reactant from the bulk, the pH condition has to be larger than 12.4. So in this white region is where I call it non-extreme pH conditions, where proton or OH minus cannot be supplied. So the next question we had was, is the buffer coming to the surface, and before reaching to the surface, the proton is released? Or proton release cannot catch up because the rate is so fast, so that it's a direct reduction of this proton together with buffer ions. It's actually important to know, because transition state, whether you calculate or you estimate together with buffer ions on the surface or not, that's very important to know. So for these ones to solve it, we can run linear free energy relationship. So pKa value is actually related to this proton. How fast the proton releases depends on this pKa value. So if the pKa value is smaller, so it's more acidic pKa, then the proton release kinetics is also faster. Likewise, OH minus is opposite, so pKa value is larger, then the OH minus release is faster. then we can estimate, at least at the double layer region where the buffer is coming, is it the free proton still involving or a direct buffer that is coming? We can see from this pKa value, so 10 milliamp per square centimeter that we are targeting. Actually, this proton can be released. Okay, let's focus on 10 milliamp, right? So if the pKa value is 765, then the free proton that is released before reaching to the surface is still the reactant here. But if you use the pKa value of greater than 7, even 10 milliamp per square centimeter, proton comes together with the buffer ions. Here is carbonate. So if you're using CO2 reduction or so on, and if your pH is about 9 to 10, then it's actually almost the things are direct buffer reduction. And even the phosphate one is about transit between you switch from the free proton or direct buffer, depending on the rate of this, the current density. So the next thing, as I said, the electrolyte property can determine the solution resistance and the pH gradient. We do nanoscale electrolysis, so we try to solve it by using COMSOL in this case. We put this nanoscale, assuming the same surface is doing the thing, so OER is here, and hydrogen evolution is here. Right? And let's see what happens in the electrolyte conditions. So this is the model that we use, so COMSOL needs to separate the meshes. So we try to use supercomputer to try to make it as small mesh as possible. Here, again, the OER, and this is, again, the hydrogen evolution. And first thing, so we have to solve it for Poisson-Nernst-Planck equations, as shown in these equations. Then we try to simulate it even far away over 80 nanometers. So Rengui was talking about this facet difference, right? But it should be much shorter than 80 nanometers, so I'm exaggerating. Even if you had 80 nanometer far apart between hydrogen evolution and oxygen evolution, yeah, so this is still less than 1 millivolt of loss. So solution resistance is something that you can definitely minimize in the case of this overall water splitting using powder semiconductors. So this is one of the most beneficial points that overall water splitting, generating together hydrogen and oxygen from the same surface. So, okay, so the solution resistance is good. So how can we confirm? So pure water versus unbuffered conditions, right? Almost similar hydrogen and oxygen evolution can be obtained. So it's not affecting. Solution resistance is not a big problem. But the next one is the pH gradient. Of course, we need to assume many things. So if we have completely static condition, ion doesn't move, but we start to generate this oxygen evolution and hydrogen evolution, and you start to develop this pH gradient, right, at the steady state. When you are working at low current density, or in this case, low, say, poor photocatalytic performance, you don't change pH, of course. But if you're really serious to achieve 10% solar to hydrogen efficiency, you started to see completely the pH gradient shift. And this shift is around pH 4. pH 4 means 60 millivolt times 4. It's greater, much greater than 200 millivolt that is required for this pH gradient penalty. So this has to be added for this band gap, right? So this has to be certainly minimized. So this is even the 5 nanometer scale. Of course, from here, you need to give the convection. You can stir it, or you can flow the water, try to minimize the pH gradient. But I would say this pH gradient using pure water cannot be neglected. So again, it's the same way as we did. So unbuffer at pH 4. We exaggerate this two-step reduction in opposite direction. And buffer, again, you use it, and then you monotonically increase it for hydrogen evolution. So that this shape is actually The same for the photocatalytic performance. So especially for this particular conditions, pH 4 or 5, hydrogen evolution side, so we use this methanol or iodate. Yeah, oxygen side doesn't change so much because water is still remaining as a reactant. But in this pH conditions, actually the proton is coming either from this unbuffered one or buffered one. Buffered one actually provides additional protons, so it improves using identical photocatalyst, using identical pH, but changing the presence of phosphate is actually helps. Overall water splitting, the story is the same. So when you are working at low current density, this diffusion is not important. It matches between the sulfate and phosphate. If you increase the light intensity, for example, or your photocatalyst becomes much more efficient, you started to see this overall water splitting, the performance difference becomes larger. This is, I think it's coming from this buffer contribution, reactant switching. So pH gradient is something that we need to start thinking about it if you want to do it for this water splitting. So how can we confirm indirectly? So we use this technique for silica deposition on this cathode material. So electrode deposition is possible, so this nitrate reduction is used to shift the pH so that you can deposit silica. And if local pH shift is indeed observed in photocatalysis, you should be able to decorate this silica very close to the platinum only. So then what we need to show, okay, first electrode deposited silica with the, this tetramethyl ammonium as an structure and directing agent. We see this 6-member ring is accumulated, and that actually makes nanomembrane on this platinum electrode. And we can see the selectivity, so the large ion cannot penetrate through this silica. You can see the ferricyanide reduction is not occurring, so this is bare one relative to it. You can completely suppress this iron reduction. But the hydrogen, the smaller molecule, can penetrate through. So there is a membrane function on this silica. And in fact, this platinum is covered selectively on this platinum. So you can see that the pH shift is actually occurring, and so that you can deposit silica close to the platinum electrode, platinum nanoparticle co-catalyst. Okay, so the last part of my talk is dedicated to why not direct measure this co-catalyst potential. It's quite challenging to see because it's so small. Right, this hydrogen evolution catalyst, oxygen evolution catalyst. But what is important to determine the rate is to measure this potential. So, of course, there are good literature. So beautiful work by Shannon Boettcher, double electrode systems. But this is still photoelectrode chemistry. So there is a pure semiconductor, and one side is only decorated for one side. And this is Frank Ostero's work. So Kelvin probe is, again, beautiful work. But still, this is photoelectrochemistry. Another one is try to measure this single particle, but still, it's not coming to the point of co-catalyst decorated on this single particle, right? So we thought we need to come up with an idea how to operando measurement of electrocatalyst on the powder systems. So then we decorate first both hydrogen and oxygen evolution catalysts. So basically, if you put this one onto the electrode, this is still closed circuit. The circuit is complete because hydrogen and oxygen are already generating from the same surface. But we still try to put this onto the same electrode of oxygen evolution catalyst. So this, in this case, is a cobalt catalyst. So blue one is a cobalt. And both decorated hydrogen and oxygen is put on this electrode. And see what happens. So basically, like I said, in this scheme, you can confirm that hydrogen and oxygen are closed circuit. You already do it in a good way, right? If the rate hydrogen and oxygen evolution 2-to-1 ratio. Actually, you don't need extra here. But what we are trying to do, put this one, hopefully part of the hole is going to this cobalt electrode. Yeah, just to show that this is typical 3-electrode system that we are using. And this is a result. So we needed to wait very long time because only the part of the hole is coming to the cobalt electrode. So we started with this open circuit potential. So you keep measuring this cobalt electrode. You start with around this one, it's cobalt redox potential. And shining the light, you shift the potential getting closer to 1.58, which is oxygen evolution potential, right? At the steady state, this particle, the cobalt oxide electrode, sees this 1.58 volt, which is the same as oxygen evolution potential. You can now remove the powders and then measure the performance just by the cobalt electrode. And this is the electrode, right? Performance, so current density as a function of potential. And what we measure was 1.58, so it's actually here. There's very little of oxygen evolution potential. Oh, this is because we wanted to minimize the accumulation of powders that doesn't have a contact with this electrode. So we wanted to have very small quantity of powders that always in contact with this cobalt electrode. Anyway, what we see is 1.58 at the steady state. And if you measure the gas evolution, so this one actually coming from the oxygen evolution from the electrode. So this point is not matching, let's say 40% only is coming from this cobalt oxide. That is okay because here you're already generating hydrogen and oxygen. So 60% is still coming from overall water splitting. Part of this hole is coming to this electrode, and that's how we say. So it matches. So we think that this way, we may be able to estimate the potential, what is happening on the surface of photocatalyst powders. So now I would like to finish by proposing a new type of morphology of photocatalysis. So when you are working on strontium titanate, actually this oxygen evolution catalyst, especially, is even if you have a bad catalyst, because the bond position is very deep, so you can still drive oxygen evolution reactions. But of course, if you come to the visible light responsive material, like we're also working on tantalum nitride, you need to have much better oxygen evolution catalyst, right? So the IV curve here should be much steeper. That means you need to put lots of catalysts. Lots of catalysts also makes the transparency lower. So we always have to think about how to design your oxygen evolution catalyst. You want to have more catalysts, but you don't want to lose some transparency. Okay, so this is what we did. So cobalt, first we make 2 electrodes. So completely different amount of cobalt that we put. So low quantity of cobalt is here, and much more cobalt. This is equivalent to 50 weight% of tantalum nitride. So you would almost cover entire tantalum nitride, right? It becomes almost black. But then we have this IV curve, right? And let's see if you put tantalum nitride on top of it, what happens. In fact, long story short, you needed to have much more oxygen evolution catalyst. So this is more cobalt that was on the electrode. And here is much less. So typically, what is missing for this visible light responsive material is not only the semiconductor materials. Yes, it's important that the carrier diffusion is very key. But additional part is electrocatalyst. We don't have enough electrocatalyst material. So we need to come up with the combination of electrocatalyst. You need to put it but it becomes black. So how do you want to maximize this performance? So we, in this paper, just accepted this inverted structure was proposed. So make electrode first. We make powder photocatalyst material, and then we put it, we together put it. So idea is, we already know how much performance you can do with this electrode. And you have to have a very good performance for oxygen evolution performance. Then you decorate this with the powders. This is already decorated with hydrogen evolution side. Hydrogen evolution is much more efficient, less over potential, so you can minimize the quantity, so you can directly put it on this powder systems. In this way, we hope that we can improve further for solar to hydrogen efficiency of 10. Right? We need to start thinking about what is the quantity that is required for this electrocatalyst side, or co-catalyst, you call it. So with this, I'd like to conclude. So transferring knowledge from electrochemistry to photocatalysis, I hope I convince you that it's very effective. Electrolyte engineering, in particular cases in neutral conditions, is very efficient. Narrowing band gap requires much more electrocatalysts together with it. And especially if you consider you want to achieve 8 milliamperes per centimeter, then probably we need to have much more electrocatalysts so that we propose this inverse structure for photocatalyst sheet. And that can be also easy to expand it, right? So you can put it in a larger scale. I want to acknowledge Professor Dome as the chair. It's very challenging for me to present in front of him, but yeah, I managed. Thank you very much for your kind attention.